This video illustrates the answers to the weekly prep for week 4 for the course Quantitative Analysis, Applied Inferential Statistics. These questions cover some basic problems related to probability from the initial set of questions in this week's reading. Specific directions can be found in the week 4 GitHub repository. Question 1 lists a number of numerical answers that represent the likelihood of an outcome expressed as a percentage. On the right-hand side is a verbal description of what those different likelihoods mean in practical terms. Remember that likelihood expressed as a percentage can range from 0% to 100%. In probability terms, it can range from 0 to 1. The first likelihood, negative 50%, does not fit in that range of 0 to 100%. We therefore choose the sixth verbal description that this isn't a realistic value, so it must be a bug in the program. The second outcome, 0%, translates to this will not happen. Any outcome with a likelihood of 0% will not occur. These are rare. Even 1 in a million events do not have a likelihood of exactly 0%. Likelihood C, 10%, is something that is not very likely to occur. So the fourth verbal description is the best fit for this answer. It could happen, but the probability is not particularly high. The next outcome D, 50%, is one that we use in everyday language. We sometimes hear people say that there's a 50-50 chance of something occurring. This roughly translates to, this is as likely to happen as not. Outcome E, 90%, is something that has a high likelihood of occurring. It is not, however, certain. This matches best with the second verbal description. The sixth outcome F, 100%, is another probability we're used to thinking about, things that will certainly happen. We sometimes overstate this. There's the famous idiom attributed to Benjamin Franklin that the only assurances in life are death and taxes. Many things that are certain are only nearly certain in reality and do not quite have 100% likelihood of occurring. Finally, the last outcome, 200%, is by definition not possible since likelihoods expressed by percentage are limited to values between 0% and 100%. This is another bug in our program. Question 2 is a classic probability problem we'll discuss in class. It involves a coin. We'll assume here that the coin is fair, so it has equal weight on both sides, and those sides are heads and tails. Since there are two possible outcomes and the coin is fair, we assume that the outcome is equally likely, 50% each. We can express that as a decimal. That's how we express probabilities. The probability of heads or tails is 0.5. We're interested in the probability of some repeated trials. In this case, a coin flipped 1,000 times. This is a key feature of many probability problems. So we'll multiply the number of repetitions by the likelihood of getting heads at each flip. And there we have it. We would expect 500 heads in 1,000 trials. Now, this might seem like an over-explanation of something that many folks can quickly work out mentally. The point here is to break down each problem into detailed steps that lay out the math and logic behind the answers. Question 3 asks about the likelihood of getting particular outcomes when we roll a die, specifically an ace. We're talking about a die that has 6 sides here, with the likelihood of getting any one of the 6 sides expressed fractionally as 1/6. Now, an ace is something that we don't often hear anymore. It's an antiquated term for the side of the die with 1 pip, or marking. So we're talking about the likelihood of rolling a 1. As with the last question, there will be what we call repeated trials. We'll roll the die 6,000 times. So 6,000 rolls times a probability of 1/6. To simplify this, we multiply the numerators, 6,001, and the denominators, there's an implied 1 under the 6,006, and we get 6,000 over 6, which comes out to be 1,000. Question 4 asks about the likelihood of a particular poker hand, a full house. I've put an example hand here. A full house has 3 of a kind, 3 sixes in this example, and a pair, 2 kings. Now, this hand is not particularly common. We expect it to occur just a fraction of 1% of the time. This question expresses that outcome in both decimal terms and a percentage, so let's start by getting everything into decimals. 1% can be expressed as the decimal point, 0.01. We can multiply that by 0.14 to get the probability of getting a full house on any one hand. That probability is 0.0014. Now, the question asks about the likelihood of 10,000 hands. We multiply 10,000 by our probability to get 14. So in every 10,000 hands, we expect a full house just 14 times. We've got a final question about lottery tickets. We want to draw 100 tickets from the box. Each box has 2 tickets in it. In box 1, there is a 1 and a 2. In box 2, we have a 1 and a 3. Importantly, we'll do these drawings with replacement, meaning that after each time a ticket is drawn, it is returned to the bucket. This means we have a 50% chance of pulling each ticket per box, and we can express this as a decimal point, 0.5. So there's a 50% chance of getting a 2 each draw or a 3 each draw, depending on the box. So which box is better? Well, since the outcomes are the same, box 2 will pay more on average, since its high-value ticket is worth $1 more than box 1's high-value ticket.